My name is Matthew, and in this video we're going to talk about implicit differentiation. And there are a couple of conditions under which we really end up needing implicit differentiation. One of those conditions is when you're working with an equation which, for example, involves x and y, where it would be very inconvenient to solve the equation for y. In other words, to make the equation say y equals, and then to start the differentiation process. The other set of circumstances is when you're taking the derivative of a function with respect to time, because again, it's very difficult to rewrite many of those kinds of equations in terms of t, where t is the independent variable and the other variable is all alone on one side of the equation. So we're going to walk through some examples and make sure that we have the fundamentals down for implicit differentiation. Maybe. There we go. So what we're seeing on this slide, for starters, is what I was mentioning a moment ago. Typically, we see our equations as y equals equations. Occasionally, I was pointing with my cursor instead of with my pen, sorry. Very often, we see equations that are written in terms of y equals. The other occasions that we have worked with are equations involving x and y, where it is possible to take that equation and solve it for y. And here's an example where that one has been solved for y. To take the derivative of that equation, you would use the quotient rule. No problem. And then there are equations that are considerably more complicated, like the ones here and the next equation, which I won't even bother circling. That would be maybe impossible to solve for y. Nothing's impossible, but it would be inconvenient to have to solve it for y. So what we do is we use a technique called implicit differentiation. And some of the time when you take derivatives, you use notation like f prime and y prime in order to indicate that you have taken the derivative. In this case, it's a little bit more typical to stick with this notation like dy over dx, and we're going to see some that are dp over dt. And the reason we like to use that notation is because it makes it very clear what it is that we're actually taking the derivative with respect to. We might see an equation that has 3 different variables, and we're not taking the derivative with respect to any of those variables at all. We might have an x and a y and a z, and we end up with dx, dy, and dz, but they're all with respect to time, so they would all be over dt. And there's not really a great way to indicate that other than using this slightly longer format, for example, dy over dx. And you're welcome to read the other text that's in there that talks about that. And then I'd like to move down into our first example. So this is a somewhat challenging topic to describe. And what I'd like to do is work through this first example, and then we'll go back and look at the details of it and talk about it, and then we'll keep going. We'll keep talking about it over and over, which is why these videos end up being slightly longer format as opposed to just a review length format of maybe 5 to 7 minutes. So here we're going to try to find dy dx given this equation using implicit differentiation. And if I asked you, what is the derivative of x to the third? My guess is that you would have no problem telling me that I should take the exponent, multiply it out front, making it a new coefficient of 3, keep the variable of x, and decrease the exponent by 1, making it a 2. And in this case, since we're taking the derivative with respect to x, and if you need to include that note in your notes, you should, what this symbol or terminology is telling us is that we're taking the derivative of y with respect to x. That also tells me, well, that's okay. Let me skip that for the moment. I'm going to keep my plus sign as I continue to take the derivative using implicit differentiation. And then the next question is, what's the derivative of y to the third? And you might say, well, that's as easy as the first term was. Take the 3, multiply it out front, keep the variable, decrease the exponent by 1. And so far you're correct, except we've left something out. There's more to this derivative. If this didn't say y, let's pretend that this says x to the third plus, I don't know, 2x squared plus 5 to the third. So you're seeing these exponents of 3 are the same, but I'm changing my y variable. Instead of having a y here, I'm putting an expression in its place. If I were taking the derivative of this term, what would be the derivative of that term? My guess is you know how to do this also. You'd take the 3, multiply it out front, just like we did down here, and you would keep the expression after it, which in this case says 2x squared plus 5, just like we kept the y after the 3. And then you would decrease the exponent by 1, making it a new exponent of 2, just like it was down here. But then what do you have to do? Well, in this example up here, the next thing you have to do is employ the chain rule. And we have to multiply by the derivative of, as I typically call it, the inner function or the inner expression, which in this case is 2x squared plus 5. So we would have to multiply by the derivative of, and I'm just going to write it like that. I'm going to write 2x squared plus 5, and we could put a prime on it, or instead of using the prime symbol, we could say that we're taking the derivative with respect to x of 2x squared plus 5. So in case that's a little small for you, depending on what you're watching this video on, that does say d over dx, which means the derivative with respect to x of 2x squared plus 5. We have to do that in our current problem also. We still need to, and I'm coming back down here now, we still need to multiply by the derivative with respect to x of our inner function, which in this case is y. And you can write it just like that, although the more typical way to write it would be like that. That still says the derivative with respect to x of y, except we typically read it as the derivative of y with respect to x. Same. So there's that notation coming into play that I mentioned we were going to probably want to use so that we know what we're taking the derivative with respect to. Okay, and then on the right-hand side of our equation, the derivative of a constant value, turns into a 0. Nice. That was the hard part. Conceptually, and this might not be true for you as an individual who's watching this video, but the person in the next room over who's also watching this and trying to make sense out of their calc homework might be saying, why are we doing the chain rule? There's only that one variable y that's there. But I'm not taking the derivative with respect to y. I'm taking the derivative with respect to x. Y is some other function. It might be that y, that's not a highlighter, sorry. It might be that y right here is 2x squared plus 5. And if it is, then I better include some kind of a note that says, once somebody tells me what that function y is, I'm going to need to multiply by the derivative of it. So says the chain rule. Okay, but because we don't yet know what y is, we don't have that y equals equation, we need to include this little note that says, once somebody tells us what it is, we could take the derivative of it, dy over dx. Okay, so that's a lot of highlighting, and as I said, that's the most difficult part. What's the easy part? The easy part is now I need to take this equation and make it read dy over dx, because the instructions said find dy over dx, so I want to be able to say dy over dx is, in other words, dy over dx equals. So let's subtract 3x squared from both sides. And then I will divide both sides by 3y squared. And if you want to put little notes out here, you can. We subtracted 3x squared from both sides, and now I'm going to divide both sides by 3y squared. And then simplify. So the 3 is canceled, the negative is sticking around, and you'll notice that I put the negative out in front of the fraction. That's allowed. The negative can stay in the numerator. I could have pushed the negative down to the denominator, or I can put the negative next to the fraction. All of those are equivalent. And we have solved for or found dy over dx, the rate of change of y with respect to x. The slope of the tangent line to the initial curve at some particular point. Which point? X comma y. So if I gave you an x and y coordinate and said, what is the rate of change of the original function, dy over dx, at this particular point, x comma y, you could take those x and y values and plug them into the right-hand side of this equation, do a little bit of quick calculation, and tell me what the rate of change of the original function is at that point. But you would need both coordinates, x and y. Let's check out another example. Again, find dy over dx given this equation, and we're being told to use implicit differentiation. You won't always be told to use implicit differentiation. Eventually, you're going to need to know that under certain circumstances that you'll need to use implicit differentiation. And again, typically, it's under two sets of circumstances. The first one being where it would be very challenging to solve an equation so that you're isolating the dependent variable. I'm looking for dy over dx again here, so dx is my independent variable. So I would want to write this equation in terms of y, where y depends on x. So I'd want the y to be all alone on the left-hand side of the equation. You might be thinking, well, that should be pretty easy to do. This is a pretty simple looking equation, except that you would have to divide both sides by x, which is no problem. But then when you take the square root of both sides, you would get y equals plus or minus the square root of 4 over x. And it's that plus or minus that makes it not really all that desirable to use that approach. So instead, we're going to stick with implicit differentiation. Let's use the product rule combined with implicit differentiation. So the product rule says, and you can do this in whichever order you want, I typically keep my first factor and then multiply by the derivative of the second one, which is the 2 multiplies out front. I keep the y, I decrease the exponent by 1, so now it's y to the first power. And then the chain rule says I have to multiply by the derivative of that inner function. Which function? The y function. And we're going to take the derivative of it with respect to x. And then the product rule says we add. Now I'm going to take the derivative of my first factor, which is the x, and the derivative of x with respect to x is just 1. And then we multiply that by the second factor, which is y squared. We're not touching that one. On the right-hand side, now that we're finished with the product rule on the left-hand side, I'll take the derivative of the right-hand side. Derivative of a constant is still just 0. And that's the hard part. So I would recommend that you come up with a way of phrasing this for yourself, whether you actually write it down or you just have it floating in your head, whatever you need to know to introduce, and specifically to know when to introduce this dy over dx. One way that you may be able to phrase it is if I'm taking the derivative of, well, in this equation we've got x's and y's. When did I need to use this additional sort of chain rule idea where I have to multiply by a derivative? The time when I had to use that is when I was taking the derivative of something other than x. And as I mentioned, sometimes it's going to be an equation that involves x and y and z, or maybe length and width and height. And we're talking about the change in volume with respect to time. Well, length and width and height, neither one of those is a time variable, which means all three of those are going to end up with a derivative with respect to time. dx over dt, dy over dt, dz over dt. So again, if you're taking the derivative of something other than the variable that's in the denominator, in this case it's an x, then you need to use that idea of the chain rule, which here we're calling implicit differentiation. All right, now the easy part, let's solve for dy over dx. I'm going to subtract y squared from both sides first. And then I will, maybe I'll divide both sides. Well, let's just do it all at once. Let's divide both sides by x times 2y. So we have dy over dx equals negative y squared over x times 2y. Couldn't you have taken this x times 2y and changed it into 2xy at this point? Absolutely. Why didn't I do that? I don't know. I figure I'll sort it out later. You could have sorted it out in the beginning. I'm going to sort it out right now. Personal preference, I guess, is the answer to that question. Simplify. The y's are going to cancel, leaving me with a negative on the right-hand side. Still going to have a fraction. I still have a factor of y on the top. The factor of y on the bottom canceled, leaving me with a 2 and an x, and here's where I'm sorting it out, and I'm writing it as a 2x in that denominator instead of x times 2. That's your derivative of y with respect to x. It's y prime. Interesting that that's y prime. I never even knew what y equaled, and yet now I have an equation that is telling me what y prime is. Let me scroll down a little bit farther and see if we can find an example of a problem that has more than just those two variables. These equations, these types of problems where you have to actually find the equation of the tangent line, I'm not going to do these with you. These you really know how to do. In order to write the equation for a line, you need three ingredients. You need an x-coordinate, a y-coordinate, and a slope. dy over dx is the slope. So you need to perform implicit differentiation, find dy over dx, just like we did back here in this problem and the problem before it. And then, as I said, you'll plug in your x and your y values to the right-hand side of those equations, and you will calculate your slope. And that will be your m value as you write the equation of your line. That equation's boring, that equation's boring. Give me an equation with more variables. Here we're finding dq dp. All right, come back. I hate when that happens. Usually that doesn't happen so soon. This is only my first video in this sitting, but I'm having to unplug and plug it back in, and usually it comes right back. There it is. So let's roll into this word problem. We're still using implicit differentiation. We've got an equation that has two variables, except it's not x and y, and we're now finding dq dp. And this gives us a chance to use our new strategy when we ask ourselves, do I have to include the dq dp right now, or do I do it when I'm taking the derivative of the other variable? Let's see how it plays out. So this is a demand equation for a certain product, and there it is. P represents price per unit in dollars. Q represents the number of units demanded, and we want to find dq dp, which is the rate of change in number of units demanded with respect to the rate of change in price per unit. So as price changes, the demand is going to change also. That's no surprise there. The more expensive something gets, my guess is the less the demand. All right, at least up to a point. So let's take the derivative of this equation. Let's find dq dp. When we take the derivative of 4p squared, I'll take the 2 and multiply it by the 4, which makes it an 8. I'll keep the variable, I'll decrease the exponent by 1, and now do I need to multiply by the derivative of this inner function? Do I need to multiply by, don't write this down yet, do I need to multiply by the derivative with respect to p of p? This is actually a really nice illustration, because if we consolidate what I just wrote right here, you would get dp over dp, which is not what we're looking for. Okay, we're looking for dq dp. Also, the rate of change of p with respect to p is certainly 1. As p changes, p changes. So in many ways, there's a good indicator that this is not the time when we need to be taking the derivative of the inner function. So that's it. It's just 8p. Plus, for the term that says q squared, let's take the derivative, multiply the 2 out front, keep the q, decrease the exponent by 1, and now do we multiply by the derivative of q with respect to p? Absolutely. We need d over dp of q. And the right-hand side derivative of a constant is still 0. Nice. All right, so subtract, divide, simplify, same as usual. I don't know why I'm having more issues than usual. All right, there it is. So let's subtract 8p from both sides before the screen goes black on me again. And this is not the time when you want to be making careless mistakes or going too fast, like talking while you're writing and making a video, because it's possible that you could mess up the arithmetic here, and that would be embarrassing. You just performed implicit differentiation, and now you're going to make a mistake on your arithmetic? I don't think so. I don't recommend it. So, unless you're good at walking and chewing gum at the same time, just make sure you're exercising the same care with your arithmetic as you were when you were trying to decide to include those extra weird factors like dq over dp. I went and put a box around this, and is that actually my final answer? It is my final answer. You might run into a homework problem that asks you to find the rate of change of demand with respect to price generally, and you would have this as your answer, negative 4p over q. And then you might be asked a follow-up question like, and what is the rate of change when price is, what would be a good number? $20. Or, yeah, that could be. So if that were the follow-up question, and you were given a price, or if you were given a particular unit demand, and that's all that you were given. You were given a p value or a q value, and you were asked to evaluate this expression. You would have to take your q value, if you were given one, plug it into this equation, then solve that equation for p. Then you would have a p value to go along with your q value. You could take the p and the q and plug them into the right-hand side of this equation, and finally calculate your rate of change, which is the left-hand side of this equation. Nice. Anything else? No, that is it. So, and actually, I believe it's in the next section that we talk about taking the derivative with respect to time. So hopefully in the follow-up video, we will be seeing examples that have more variables and are a little bit more complicated because we'll be taking the derivative with respect to a variable that's not even there. Of course, as we know, time is always against us. It's kind of a variable, but it's kind of a constant. But now we're getting philosophical. So I'll stop and I'll see you in the next video. Thanks for hanging with me on this one.